Welcome. Today we're going to learn about the washer method revolving around the y-axis. So in this situation, this example, we have an area or a region. If you look at our graph, you'll see a striped area. And we are going to take that and revolve it around the y-axis. The y-axis is our axis of revolution, we call it. When we do that, we will actually create a volume. And there are a lot of great videos that demonstrate the animation of that on the web. But in the meantime, we're going to just focus today on the actual calculation. So the integral looks like what we have in 5. So if you go to 5, that is the integral that's going to create this volume. You're going to have an outer radius and an inner radius. The outer radius is the large R of y, and the inner radius is the small r of y. And that's why we call it the washer method. You've got an outer and inner radius. Okay, so let's go back to our diagram. We have a rectangle that's been drawn on our diagram, and you want to use that rectangle to actually come up with the various calculations. This rectangle is going to be perpendicular to our y-axis. That's the axis we're revolving around. And once you get that set up, which we have in the diagram, the next step is, if you look at 2, you'll see the short end of that rectangle is a vertical distance, and that is going to represent our dy. If that short end had been a horizontal distance, it would represent our dx. But since it's dy, that tells us that our integral will have everything with respect to y. So I don't want to see any x's on our integral. Everything has to do with y. Okay, so that's key. Now, the next thing we want to do when we're, again, assembling our integral, we need the limits, okay? So if you look at the region that's striped, since we're dealing with y, as I said, we would want the y limits. So the bottom is pretty obvious because it touches the x-axis, so that would be y equals 0. But the top of the region is not so clearly defined. So we have to use our equations to determine that. If you look at 1, we have x equals 2 there, and on the left we have y equals square root of x. Now we're going to use both of those equations and essentially set them equal to one another to figure out our y limits. But unfortunately we can't do that unless the first equation, y equals square root of x, is solved for x. So if you solve that for x, you're going to get x equals y squared. And then you're going to set that equal to x equals 2. So I do that in step 6. If you look at 6 on the left, you'll see I set 2 equal to y squared, and then I solve y and I get plus or minus the square root of 2. Now we're just going to use the positive side, the square root of 2, because the bottom of our region is not negative, it's 0. So our limits, our y limits, are going to be between 0 and square root of 2. And that's important for our integral. Okay, so what else do we need? We need the outer and the inner radius. So that's the next step. So go back to the diagram, and if you look at 3, item 3, that represents our outer radius. And if you follow the arrows on the left side, our radius touches the axis of revolution, in this case the y-axis, and the right side of the arrow touches, in this case, x equals 2, so 2. And if you want to calculate that, you would, since it's a horizontal measurement, you calculate horizontal measurements right minus left. So the right side touches 2, so that's 2, and the left is the axis, which is just 0. So the difference is our outer radius, which is 2. And I've listed that in item 7 on the left side. Now we want to focus on the inner radius. So go back to your diagram and look at item 4. Small r of y represents their inner radius, and that is the difference between, you can see the left arrow touches our y-axis again. The right arrow is the closer side of our rectangle. Okay, so the outer radius goes from the further side of our rectangle to the axis of revolution, the inner radius from the closest side of our rectangle to the axis of revolution. Okay, and again, if we want to calculate the inner radius, we calculate, since it's a horizontal measurement, right minus left. So if we go to the right side, that rectangle touches the graph. Okay, so whatever that is, and I'll focus on that in a second, minus the left side, which is just our axis, so that's just 0. Okay, so the left side 0, so we don't have to worry about that, but the right side is our graph. Now, if you go back to 1, you'll see that is represented by y equals the square root of x. Well, the problem there is I can't use square root of x in my equation, in my integral, because everything has to be in terms of y. So I have to solve for x. So x will wind up being, in this case, y squared. And that's what I'm going to use. I'm going to use y squared in my integral. So if you go again to the left side, you'll see item 7. The inner radius, or the small r of y, is y squared. Okay, now we really have all we need. So if we go to item 8, we have our limits that we talked about from 0 to square root of 2. We have r squared, the outer r squared, so that's 2 squared, minus the inner, which is y squared squared, which is y to the 4th, and then we have dy. Then in item 9, we actually calculate our integral, as you can see, and then in item 10, we get our answer. That represents our volume. So what are the steps for this? Okay, so in 1, we draw a region, we use the given equations that bound the area. In 2, we draw a rectangle perpendicular to the y-axis, our axis of revolution, within the striped region. 3, since the short side of the rectangle represents a change in y, we make sure the integral is in terms of y and has a dy. 4, calculate the y limits. 5, calculate r of y. 6, calculate the other r of y, the inner radius. 7, we substitute everything into our integral below, and we solve. And that is the washer method, revolving around the y-axis. So now go practice, practice, and practice some more.